Hello everyone. I am going to show you, I promised this a few days ago, that I would show you where some of the kinematic equations come from based on the graphical techniques. As you know from lecture, I've tackled most of these one-dimensional problems using graphical methods. Most of you know of equations to do this, and you'll find those in Chapter 2. And I just want to show you how the equations come out of the graphs. I think the graphs are better. I think they make you think a bit more about the problem. But I want to quickly here show you where you can get some of the more basic kinematic equations out of looking at the graphs if we just use symbols. So here, let me fire this up. Let me get my pen going. Let me try a different color today. Let's go to that. And let's see if this is working. Boom, boom. Okay. Now, one thing to remember, if the definition of acceleration is delta v over delta t, where acceleration and velocity are vectors. Now, let's look at this in one dimension, and we can basically drop the vector notation and we can say this. These equations are valid in more dimensions. We're just deriving it for one dimension. Now let's rearrange that, and we can say that delta v is equal to a delta t. And I think what I'm doing right now you would have seen in a Khan Academy video, but I'll just replay it here. It'll only take a second. Now remember what deltas mean. It's basically a final velocity minus an initial velocity is equal to a t final minus t initial. Now just suppose, and we're free to do this, let's just say that v initial, let's call it v naught, and let's say that occurs when t is equal to 0. So we're gonna look at an equation where at t equals 0 it has initial velocity of v0. Might be 0, it might be something else. So we then can write that v final minus v naught. So we're just using a specific, not just a definite range, v final minus v initial, but we're going from v final back down to a velocity that corresponds to 1 time equals 0. Just makes the equations a little bit more convenient. And we can write t final minus 0, because we're saying that because this time corresponds to that velocity, and t equals 0 when velocity is v0. So then we can write v final is equal to a t final plus v naught, and we can actually drop the subscripts for the v's, and it's assumed that this is a future time. We can write this like that. And that's one of the basic kinematic equations right there, where again this is the velocity at t equals 0. And you can see it's true. If you put 0 in there, then you simply have v equals v naught. Now let's take this graph and let's make a graph. Let's do velocity. Let's do time. This will be in seconds. This will be meters per second. And if I graph that, I see something like this, where this is v0. And let's go to some future time. We'll just call it t. And one thing to note, that's going to correspond to right here. Let me just write it over here. I'm going to call this some v final. And I hope you know this from class. Talked about it a lot. This area bound is delta x. That's the displacement between 0 time and some future time t. So how do we evaluate that area? Well, let's actually break it up into two areas. Let's call this delta x1. We'll call the top area delta x2. And notice we have a rectangle and we have a triangle. So if I want to get total delta x, it's going to be delta x1 plus delta x2. And let's try this. For delta x1, notice we have this, again, we have this rectangle. Its area is t. It's really, if you want to be totally correct, it's t subtract 0. That's the length of the bottom part. And its height is simply v naught minus 0. And then it's plus the top one is a triangle. Almost said rectangle. It's a triangle. That has a base. Should remember we do 1/2. We do the base, which again is just t. All right, it's just t because I say I'm going to run out of space. And this is going to be v final minus v initial. Let me just put a little so you get that confused. So we have basically v naught t. That's what those amount to. I rearranged them. Plus 1/2 t v final minus v initial. You might wonder, okay, what are we going to do with that? Well, let me go to another page because it's getting a little cramped here. So I can write that delta x, again, just to repeat what I have, v naught t plus 1/2 v final minus v initial times time. Let me just verify that I wrote that right. Yes, put the time in a different spot, but it's the same thing. So there you go. But remember, from the previous equation, we had written this, where in the end, on the other page, I didn't have a subscript there, but this was the equation. Well, if this is that, let's put this in for that. So here we go. Delta x is equal to v naught plus, sorry, forgot the t, plus 1/2. And it's going to be v naught plus at minus v naught. Simple as that. And again, here's my t. And notice that this would cancel with that, and we have delta x is equal to v naught t plus 1/2 at times t, which is simply v naught t plus 1/2 at squared. And since delta x is equal to x final minus x initial, where this is the same deal, this is actually, you can write that as x0, which is the position at t equals 0. We can then write, we can go and we can say that x is equal to x naught plus v naught t plus 1/2 at squared. And that should be familiar to everybody. Again, notice if you put 0 in for t, this equation reduces to x equals x0. So it gives us our position at time t equals 0. But this is also one of the key kinematic equations. So if I just write down what we have, on the first page we showed this, and we just proved this. Probably the biggest one. And I bet you have seen in your textbook that you can write this, that this is also a popular equation. Well, I can tell you if you take this And actually, if you leave this as x minus x naught, which is just delta x, as this. So if you use this, if you take this guy, rearrange him, guess him, her. If you look at this, you can write this. If you want to have t all by itself on the left, you can then, notice there's t here, and there's t there. If you take this, and put it in there, and put it in there, let me just write the first step you would have. And it looks a little crazy at first. Looks big. If you do this, if you now expand this out, this is a square, you multiply this through here, and you simplify, you will discover, notice we've eliminated time, notice this has no time, you will discover that equation there. And that these are the three biggies, and this is where they come from. And what that took 2 or 3 pages, so it's not very hard to do. So they're not magical, they come from common origins. Okay, I don't want to keep you too long, so I think I'll finish it up. I'll keep that. So I will see you guys later.